Now this process for acids and bases it obviously involves the production of ions in solution. So if we just look at acids for a second, sort of like solubility or dissociation of ionic compounds, we've got a new scenario in aqueous solution than we had previously. When acids, the molecules that make up acids, when they break up in aqueous solution, we refer to them as they're ionizing. So when they form an H plus or H3O plus ions in solution, and also the corresponding anions, we refer to that process of ionization. Slightly different from dissociation because, of course, ionic compounds were ions previously. We're not making ions, but with acids and weak bases, they were not ions before they went into solution. Now that there are ionized species, we refer to that process as ionization. Now, it turns out that the percentage of the molecules that ionize varies from one acid to another. And this is what we refer to as strong and weak acids. Strong acids are acids that ionize 100%. Okay, so if we have our HCl molecule, and if we use the Arrhenius definition, just going to produce an H plus ion in solution, H plus aqueous plus Cl minus. Let's clean that up a little bit. Plus Cl minus aqueous. 100% of the hydrogen and chloride ions are on the right side of this equation. There are no HCl molecules in solution. Is it 100% ionized? Weak acids, let's take a look at, say, formic acid, HCH2O. If we look at it from the Bronsted-Lowry definition, we'll say that it donates a proton to the water molecule, of course making the hydronium ion, and the formate polyatomic ion, CH2O-. Notice that we drew back and forth arrows to indicate equilibrium because there are weak acids ionized less than 100%, often much lower than 100%, a percent or less. So we have some formic acid in solution and some formate ions in solution. We have both, so we have to indicate that we're at equilibrium eventually with both of these species. The same can be true for strong bases. Strong bases ionize or dissociate 100%. Weak bases ionize less than 100%. If we go back to think about our electrolytic solutions, that's what came up with, that's what produced our weak electrolytes solutions. Our weak acids or even weak bases produce weak electrolytic solutions, meaning that we go back and forth. Here's the Arrhenius definition for acetic acid. Okay, meaning that it goes back and forth with the H plus ion. And notice that a very important aspect is that the polyatomic ion doesn't ionize or break any bonds in there. Just the hydrogen is donated into a solution. And again, the big difference between those is that they conduct electricity, but not as well as a strong electrolyte, which now would be any soluble ionic compound, any strong base, or strong acid. Okay, so now if you add a acid, any molecule that can ionize and produce the H plus or hydronium ion, to a base, any product or compound that produces hydroxide in solution, what we have is a neutralization reaction. The acid and base will neutralize each other to make a primarily neutral solution. The net ionic equation for most strong acid, strong base equations is H plus OH minus yields water. And we'll take a look at a couple of examples that show why this occurs. Okay? When predicting the products of acid and base neutralization reactions, we know that the H plus from the acid is going to combine with the hydroxide from the base to produce water. So a simple mechanism for predicting the product would be this general statement that an acid plus a base equals a salt, remember any inorganic ionic compound, plus water. We can also use the mechanism for a double replacement reaction, which we'll see next. Okay. At the end of this unit, we'll go over solubility rules. But again, the salt that is produced will be soluble based on those rules. Generally, strong acids and strong bases will produce soluble solutions or soluble salts in the solution. So here we have the reaction with hydrochloric acid and sodium hydroxide. An acid plus base equals salt, in this case table salt, plus water. Now, sodium chloride is aqueous in solution, meaning that it dissolves, dissociates into its corresponding ions. And so what we could see is that if we broke this up into its net ionic equation, we would see that sodium and chloride are both spectator ions. So the net ionic equation for this reaction would be H plus hydroxide yields water. Okay, let's take a look at a couple more examples to illustrate this and figure out the how to predict the products for acid-base reactions. Okay, so now we have a reaction between aqueous nitric acid and aqueous calcium hydroxide. And what we'd like to do here is utilize our skills to determine the molecular, ionic, and net ionic equation for this. Okay, so the first thing we're going to do is calculate or determine the molecular equation. So we have to remember that nitric acid is HNO3 because, of course, nitrate is NO3 minus, and that's what dictates the fact that it is the nitric. 8 becomes ic, naming mechanism for acids that we learned several units ago. So HNO3 aqueous plus calcium hydroxide, we know that's going to be CaOH2 aqueous. Okay, we want to be able to predict the products. So we know that an acid plus a base equals salt plus water, so we're going to have a water molecule over here. Now what salt we do, we can actually use the double replacement mechanism by thinking about what ions are composed here. Of course, nitric is HNO3, so that's H plus and a nitrate polyatomic ion. And then we have calcium 2 plus and hydroxide. Okay, we know that the H plus reacts with the hydroxide. And basically what we're doing here is we're switching the cation and anions because we know that anions aren't going to react and cations aren't going to react because of the repulsive electrostatic forces. Okay, so our new compound will be calcium nitrate, and so CaNO3 2, that will be aqueous. Okay, and of course we're going to have to balance that, and we've got 2 nitrates over here and only 1 over here, so we're going to have to do 2 here. Now we've got 2 hydroxides, 2 hydrogens, so we're going to need 2 here. If we do the ionic equation, complete ionic equation, what that will look like is breaking up all of these into 2H plus aqueous plus 2 nitrates plus calcium 2 plus aqueous plus 2 hydroxides aqueous. Not sure why I started parentheses there, but you don't need that. Yields calcium 2 plus 2 nitrates plus 2 waters. And remember, those are liquids, so that's not aqueous. We don't have to break those up. So what of our species here were spectator ions? The nitrates didn't do anything. Neither did the calciums. Okay, and so what we're going to have is our net ionic equation looking like 2H plus 2 hydroxides aqueous yielding 2 water molecules. And if you look at this, you can see that all of these values are divisible by 2, and so this can boil down to our net ion equation. H plus OH minus yields us water. Okay, So one more example of this. Let's just predict the products and balance the equation for this reaction between hydrochloric acid and barium hydroxide. Okay, again, we know that there's H plus and Cl minus from the aqueous, and then Ba2 plus and OH minus from the barium hydroxide. Okay, so if we have H plus and OH minus reacting and Cl minus and Ba2 reacting, we will get barium chloride and water liquid, aqueous, aqueous, and then we'll just need to balance it. Because of the 2 hydroxides, we're going to need a 2 here, and because of the 2 Cls, we're going to need a 2 here. And that's our balanced chemical equation that predicts the products from an acid-base neutralization reaction.